Hi everyone, my name is Formalizing from Bear Science Lab, and welcome back to Quantum Mechanics. Today, we'll be talking about spin. Now, contrary to the expectations, spin is actually not as mystifying as I expected when I was first going into quantum mechanics, and it's probably not going to be as mystifying as you expect either now that we've come this far. Now, after the very droning and long, boring video on angular momentum, spin is essentially the culmination of all of that hard work. Now, recall that in that video, we talked about the eigenvalues of the angular momentum z component. And we mentioned that they could be h bar times any half integer, minus a half, 0, half, 1, 3 halves, 2, and so on and so forth. Now, spin is just that, just those eigenvalues, those half integers. Now, spin at its core is the intrinsic discretized angular momentum of a particle, but that makes no sense. We talked about Bohr's equation a long time ago, and you can essentially imagine spin kind of like the energy levels of a particle dictated by Bohr's equation. So the particle in the hydrogen atom, the electron, starts from minus 13.6 electron volts. It's forced to go to minus 13.6 over 4, then it's forced to go over minus 13.6 over 9, etc. It's not able to go anywhere in between. There's a discrete set of steps, and it has to follow them. Just the same way, there's a discrete set of steps for angular momentum, too. But while an electron can change its energy levels, a particle sticks with its spin for life, if a particle has a life of any sort. So a particle's spin is an intrinsic property of itself, just like its mass or its density. So that's what spin is all about. But is the lecture over? Not yet, because we still need to formalize our notions. So what is spin? Well, as I mentioned before, it works kind of like the energy levels in the hydrogen atom, except you can't change the spin either, but it's a little bit more than that. Remember that when we were solving these equations, we get that lambda 1 is equal to mh bar for some half integer m, and lambda 2 is L times L plus 1 h bar squared, where L is some integer. So with these, spin is essentially the exact same as this. But instead, we're writing spin z f, and it's not going to be f very, very soon. Well, it is still f. I'm lying there. mh bar f, this equation, as well as s squared f being equal to L times L plus 1 h bar squared f. All right. Now, the interesting part. The raising and lowering operators. So remember that the raising operator is equal to Sx plus Isy, and the lowering operator is the opposite. I'll just put a plus minus there. Now, first things first, that means that Sx can be expressed as half S plus plus S minus. And that also means that Sy can be expressed as well, Isy plus Sx and Isy minus Sx. So this is S plus, and this is minus S minus, which means that it can be represented as 1 over 2i times S plus minus S minus. So there we go. Sx is this, Sy is that. But things get a little bit deeper than that. You see, how do we actually express S plus and S minus? Well, remember that S plus and S minus are equal to sx plus is, well, I already said that, plus minus isy. What happens when you square them? You get sx squared plus, well, plus minus sy squared. Is it actually plus minus? No. What happens when you square sx plus minus isy squared? Well, you get sx squared plus isy squared, which is actually minus sy squared, plus minus 2isxsy. Now that is a very concerning chunk, which means that while we have these two, well, we'll see what the raising and lowering operators actually look like in just a minute. For now, let's talk about what is f, or what f actually is. Now, first of all, we're going to be studying a specific kind of spin in this video. Now, spin, as I said, can be 0, a half, 1, 3 halves, and so on and so forth. And today, ironically, 0 is not the simplest. But not just that, 1/2 is the spin that almost every single particle in the universe takes on, including the most important ones, the proton, the neutron, and the electron. So we're going to be studying half spin, not just because of that, but also because it's extraordinarily simple. It can only take on 2 states: spin up, half-half, and spin down. So let's call this, I don't know how to draw chi. Spin up, and let's call this spin down, half minus half. So this, or these right here, are the 2 states of any spin up and spin down particle. And whenever we see any particle, we already 100% know if they're in spin up or spin down. That doesn't mean, however, that we know a lot of other things about it. Its spin x, spin y, and spin z components are totally up to chance, and we'll see that in just a bit. So now, here's the second thing. We're going to be representing the state of these particles as a vector. They're not really vectors, they're something we call spinors. The theory of spinors is very complicated on its own, so we're not going to talk about it today. I don't understand it, but we're just going to keep it short and say these are not vectors, but we're going to treat them like one for the purposes of today. So we get half-half for spin up and half minus half for spin down. Just like a wave function from earlier was telling us the state of most particles, these guys are going to be telling us the state of the spin of a particle. Alright, so now, naturally, since we're using vectors instead of functions, you're probably more familiar with eigenvectors instead of eigenfunctions, and that means instead of an operator solving things, it's going to be a matrix solving the equation. So where does the matrix come from? Well, actually, that's relatively easy to work with. Since we're doing a 2x2 matrix, that makes things even easier to work with by brute force. I don't even have to put effort into actually solving the eigenvalue equation, which means that we can take SZF is equal to MH bar F, and then say, well, F is going to be equal to LM. Then what is SZ? Well, let's say it's a matrix A, B, C, D. I don't know. Who knows? And that matrix is going to give us A, B, C, D times LM is equal to MH bar LM. And in our case, the LM in question is half-half, and we get returned half H bar, half-half. Now, there's the other side, which is what happens when we take half minus a half. And we'll look into that very, very soon. So what do we get on this side? Well, we get half A plus half B, half C plus half D. No big deal. Is equal to half H bar, half half. Now, when you multiply both sides by 2, you get a plus b is equal to h bar over 2, and c plus d is equal to h bar over 2. Great, we have 4 unknowns and 2 equations. That's not going to work. So we have to take into account the other possible spin state. Spin down. Once we do that, we get a set of totally different equations. Not totally different. We get this is equal to minus this minus this. And what does that tell us? Well, that tells us that half, or a minus b, is equal to minus h bar over 2. And it also tells us that c minus d is equal to h bar over 2. Hey, wait a minute. That means b is just h bar over 2. C is minus h bar over 2. Wait, no. Sorry. B is minus h bar over 2. C is h bar over 2. And the other two components are 0. Which means that the LZ matrix has to be what? H bar over 2 multiplied by 0, 1, 1, 0. Also, now that we know all of this, I'm tempted to show you the actual raising and lowering operator equation, which are just equal to, Lm is equal to the square root of L times L plus 1 plus M plus minus 1 times L M plus minus 1. Notice this is the only one where things change because this is the raising or lowering operator. It's actually going to raise or lower the state. And as you can see here, if we subtract 1 from the up state, it's going to go to the down state, and vice versa. If we add 1 to the down state, it's going to go to the up state. And I think that's pretty obvious, actually. I shouldn't have mentioned it. So, we know that now. First, let's figure out what L squared is. And maybe that'll tell us something about Lx and Ly. Now, L squared, F, or Lm, has to be equal to M times M plus 1 Lm. So, what happens when we open this up? Well, we assume L squared is also ABCD times Lm is equal to M times M plus 1 Lm. And so what? Well, we get AL plus B. Oh, sorry, we can't do anything without plugging in values. So let's take spin up first. Hold up. I changed L. Oh, oops. There's no minus sign here, is there? Whoops. So half A minus half B is actually equal to H bar over 2. And okay. Sorry. So this is true, this is false. This is what? Half C minus half D is, or C minus D is equal to minus H bar over 2. Okay, so wrong. B is equal, A is equal to H bar over 2, and D is equal to H bar over 2. The rest is 0. So this is actually the identity matrix. Oops. So back to solving this equation, we get what? Well, this is going to become M plus 1 here is 3 halves, which means we get A over 2 plus B over 2, or A plus B, is equal to 3 halves L. And once again, this is going to be unsolvable until we look at spin down. We can't do anything with 4 unknowns and 2 equations. So we turn this into a minus, and this is going to be M plus 1, which is just 1 half, which means this side is going to be minus 1/4. And so we get, and this is minus half. So we get A minus B is equal to minus half L, and C minus D is equal to, and now things get seriously spooky because I have to prevent myself from making a dumb sign error. This is half, why did I say half L? Half L H bar squared. L is actually equal to half, so this is minus 1/4. And here we get half minus a half. So this gives us half c minus half d, or c minus d, is equal to 1/4 h bar squared. Okay, so this gives us a little bit more information on what we're working with. Because now we know that 2c is equal to h bar squared, and so c is equal to h bar squared over 2. And on the other side, we also know that 2a is equal to 1/2 h bar squared, and so a is equal to h bar squared over 4. And what does that tell us? Well, b is equal to c, and that also tells us c is equal to a. Oh, wait, no, d is equal to a. Oops. Which means that we get the matrix h bar squared over 2, or no. We get the matrix h bar squared over 4, h bar squared over 2, h bar squared over 2, h bar squared over 4. Or in other words, h bar squared multiplied by, or h bar squared over 2, half 1, 1/2. So that's L squared. Now we can also talk about L plus and L minus. And using those, we can finally find the matrices for Lx and Ly. So where was the L plus and minus formula? Okay, it's over there. Let me do a little bit of blackboard magic here quickly. Okay, no, that's still not high enough. Let's push this guy to the roof and this guy just below it. Still not enough space. What can I do? Well, I can lift it up a little bit more. Okay, that's enough. So we get L plus minus Lm here. Let's do a half is equal to the square root of 3/4. Oh, there was an h bar here. Oops. Plus m times m plus 1 is equal to 3/4 again. And, well, isn't there? Oh, there's a plus minus 1. Okay, so it's going to be half multiplied by half plus minus 1. And that just, no, that's not. It's 1 plus minus 2 over 2. Which means it's actually 1 plus minus 2 over 4. Which means this is actually 4 plus minus 2 over 4, or 1 plus minus a half. So that's what we're working with so far, multiplied by half, and what was over here was m plus minus 1, which means we also have half plus minus 1. So what do we get out of this nonsense? Well, we have to solve separately for L plus and L minus, of course. L plus, let's call it A, B, C, D. You can see I'm being very creative with the matrix names here. Half is equal to the square root of 1 plus minus a half multiplied by h bar, half over half plus minus 1. Well, it's going to be plus 1, which makes this 3 halves in our addition. And 3 halves over there, too. So that's the plus operator. And so what do we get here? Well, we get a, b, 1, so right there, minus. A plus b is equal to the square root of 3 over 2 h bar. And similarly, c plus d is equal to the 3 times the square root of 3 over 2 h bar. Now, we still don't know anything unless we take the minus version, which gives us minus here, and it's going to be 1 half minus 1, which is minus a half there. And so, I mean, things are actually looking a lot cleaner here. A minus b is equal to the square root of 3 over 2h bar. And c minus d is going to be equal to, there's actually going to be a difference this time, the square root of 3 over 2 minus the square root of 3 over 2h bar. Okay, so it looks like the difference between adding d and subtracting d. So c is equal to 2 times the square root of 3 over 2h bar, and hence d is equal to half of c. Meanwhile, it looked like b is equal to 0 because it made no difference whether we were adding or subtracting, and a is equal to the square root of 3 over 2h bar, or being equal to d, which means that at the end of the day, everything was just this is equal to 0, this is the square root of 3 over 2h bar, this is the square root of 3 over 2h bar, and this is 2 times the square root of 3 over 2h bar. All right, so now we still haven't done L minus. Okay, so what happens when we do L minus? Well, then we have to change up our strategy a little bit. We start with half-half. So this is no longer equal to 3 halves. This is now equal to 1 half. Yes, that's scary. We almost saw an imaginary number for a second. And that's h bar, half minus a half. Things are going fine so far. Oh, shoot. It should be 3 halves. Sorry. Oh, God. Okay. So now, in this case, we take a plus b is equal to the square root of 1 half multiplied by h bar. Then c plus d is equal to 3 times the square root of 1 half multiplied by h bar. Then we have a minus b is equal to the square root of, okay. Sorry if I haven't done this. This should be 1 half. Oh no, it should be minus a half. So we get a minus b is equal to the square root of half h bar, and c minus d is equal to the square root of, minus the square root of half h bar. Now that allows us to solve once again and see that b is equal to 0, and a is equal to the square root of half h bar, and c is equal to 2 times the square root of half h bar, which means that d is equal to the square root of half h bar. Okay, so what does that mean? Well, L plus has ended up being rad 3 over 2 h bar 0, 2 rad 3 over 2 h bar, rad 3 over 2 h bar. Meanwhile, L minus has ended up being rad half h bar 0, 2 rad half h bar, rad half h bar, which means that it looks like L plus is just rad 3 L minus. And so what does that mean for us? Well, Lx being just half L plus L minus is going to be half times L plus times 1 plus the, well, not 1 plus the square root of 3. It's L minus multiplied by 1 plus the square root of 3, which gives us 1 plus the square root of 3 over 2 multiplied by that matrix. The square root of half h bar, 0, the square root of 2h bar, square root of half h bar. And y, which is going to be 1 over 2I, oh no, that's an imaginary number, that's scary, times L plus, times L plus minus L minus, I just have to check, yeah, S, it should be S, everything has to be S. Is equal to 1 over 2I S plus minus S minus, which is equal to 1 over 2I times 1 minus rad 3. Well, not 1 minus rad 3. Let's say, if I factor out S minus, it's rad 3 minus 1. The square root of half h bar, 0. The square root of 2h bar, square root of half h bar. Which means that we've successfully figured out all 3 of the components. Now, here's the problem. When we try to when we try to measure the eigenvalues of these things, here's the problem. They're going to change on every measurement. On one measurement, they're going to be h bar over 2, and on another, they're going to be minus h bar over 2. Actually, those are the only 2 values they can take. But there's no certain way to know what the value is before you measure it. And there's no certain way to know if your measurement was right or, just another coincidence. So this is the big problem with, well, it's not a problem. It's just the quantum reality. You can't perfectly know a result. And when you measure something, you've only figured out a measurement. How do you know that your measurement hasn't disturbed the particle or the particle didn't take a position just for your own measurement? So that's all about spin.